Have you ever wondered how a reddish rock, mined in different corners of the planet, can be transformed into the aluminum we use every day? From soda cans and kitchen paper to airplane fuselages and satellites orbiting the Earth, this light and strong metal has become a mainstay of modern life. In this step-by-step tour, we'll discover how bauxite is converted into alumina, how electricity produces metallic aluminum, and how huge factories mold it into coils, sheets, and pieces that end up in our hands. Every year, humanity produces more than 70 million tons of aluminum. To put that figure into perspective, it's equivalent to manufacturing more than 9 kilos of aluminum for every person on the planet. But behind this shiny light metal lies a story that begins with an earthy, reddish mineral: bauxite. Bauxite is the main source of aluminum. It is found mainly in tropical and subtropical regions such as Australia, Guinea, Brazil, Jamaica, and India. To obtain 1 ton of finished aluminum, an average of 5 tons of bauxite are needed. This means that mining this resource must be carried out on a large scale and with enormous technological deployment. The process begins with land preparation. Large excavators remove the surface layer of soil and vegetation to access the deposit. Once the rock is exposed, holes are drilled in strategic locations where explosive charges are introduced. These detonations fragment the bauxite into smaller, more manageable pieces. After blasting, the remains are collected by mechanical shovels and mining trucks that can carry hundreds of tons in a single trip. To sort the materials, 2 main techniques are used: side casting, moving the fragments to the sides of the trench; stockpiling, accumulating the rock in large piles classified according to size or quality. This first step is crucial because the continuity of the entire industrial process depends on the efficiency of extraction. Once extracted, the bauxite must travel long distances to the refineries. Transportation can involve conveyor belts, trains, trucks, and finally ships that carry enormous shipments to plants located near the coast. At ports, the bauxite is loaded onto deep draft vessels, each capable of carrying more than 80,000 tons. It is then unloaded at industrial terminals and taken to processing plants where the real transformation begins. This is a key point. Bauxite in its natural state cannot be used directly to make metallic aluminum. It must first be converted into an intermediate material, alumina. The first chemical step within the plant is known as digestion. Here, crushed bauxite is mixed with caustic soda, sodium hydroxide, in a huge reactor called a digester. The caustic soda dissolves the aluminum compounds present in the bauxite, especially the aluminum hydroxide. To accelerate the reaction, the mixture is subjected to high temperatures, between 150 and 200 degrees Celsius, and pressure. The result is sodium aluminate, a soluble compound that will be the basis for obtaining the white alumina powder. This process was developed in 1888 by Carl Bayer, an Austrian chemist. His method was so revolutionary that even today, more than a century later, it remains the basis of the aluminum industry. The resulting sodium aluminate undergoes a precipitation step. To achieve this, small particles called seed crystals are introduced. These act as nuclei to which new aluminum hydroxide molecules adhere. The process takes place in giant tanks with trays and controlled agitation systems. Over time, the seeds grow into larger, purer crystals. Once they reach the desired size, the crystals are separated from the remaining liquid. This step is vital because it ensures that the final alumina has a purity level high enough for the next stage. Once the aluminum hydroxide crystals have formed, the next challenge is transforming them into a stable, useful material for the production of metallic aluminum. To do this, the crystals are introduced into calcining furnaces, large structures designed to withstand extreme temperature conditions and maintain a continuous process. During calcining, the aluminum hydroxide is subjected to intense heat that can reach 1,000 degrees Celsius. This increase in temperature causes the thermal decomposition of the compound. The water contained in the crystals evaporates, and at the same time, impurities that could affect the quality of the final product are eliminated. The result of this process is a very fine white powder known as alumina, aluminum oxide, L2O3. Although at first glance it may resemble flour due to its light texture and uniform color, it is actually a material with very different properties. Alumina is extremely heat resistant and constitutes the most important intermediate point in the entire aluminum production chain. To obtain metallic aluminum from alumina, the Hall-Héroult process is used, developed in 1886 by Charles Martin Hall in the United States and Paul Héroult in France. The alumina is dissolved in molten cryolite, a salt that lowers the compound's melting point. It is then placed in large electrolytic cells where a direct electric current is passed. In these cells, oxygen is released and reacts with the carbon in the anodes, while pure aluminum settles to the bottom in liquid form. Each cell can produce several tons per day, but also consumes enormous amounts of electricity. In fact, it's estimated that manufacturing a single ton of aluminum requires up to 14 megawatt-hours of energy. That's why many plants are located near hydroelectric dams or other abundant and inexpensive energy sources. The liquid aluminum, which emerges at over 700 degrees Celsius, is carefully extracted with ladles or pipes and poured into steel molds. Depending on the size, small ingots weighing just a few kilos or industrial blocks weighing over 30 tons can be produced. During casting, care is taken to ensure that no air bubbles or residues enter. The metal is then allowed to cool slowly until it solidifies. Once finished, the ingots are removed by cranes and stored in special tanks. Each ingot bears a code that allows its origin, composition, and production date to be traced. Once the aluminum ingots have been melted and solidified, they are not directly used in industry. To convert them into useful materials, they must first undergo a transformation process that converts them into thinner, more malleable sheets, coils, or profiles. The process begins with the preheating of the ingots in specialized furnaces that reach temperatures exceeding 500 degrees Celsius. This step is crucial because the heat makes the metal's internal structure more flexible, facilitating subsequent thickness reduction work without the material cracking. When they reach the appropriate temperature, the ingots are transferred to reversible mills equipped with enormous rollers that apply forces equivalent to thousands of tons of pressure. These rollers rotate in opposite directions and progressively compress the aluminum, reducing its thickness with each pass and elongating it into a continuous sheet. The process can be repeated several times until the desired size is achieved. An ingot just a few meters long can be transformed into a sheet that stretches for kilometers while maintaining the strength and uniformity of the material. Finally, the resulting sheets are rolled into giant coils, which facilitate transport and storage. These coils represent one of the most versatile forms of aluminum packaging and are shipped to factories around the world, where they will be used to produce everything from cans and containers to structural components for airplanes, automobiles, and electronic equipment. This step is key because it marks the transition from aluminum in its primary state to the material ready to enter the production lines that are part of everyday life. Aluminum has earned the title of one of the most versatile and ubiquitous metals in our daily lives, and we only have to look around to notice it. We find it in the beverage industry, where millions of cans and containers are manufactured every day thanks to its lightness, strength, and infinite recyclability. We see it in construction, shaping windows, door frames, roofs, siding, and entire structures that take advantage of its durability and surprising ability to resist corrosion. We feel it in aeronautics, where every airplane fuselage and wing depends on this metal because it allows us to fly lighter, consume less fuel, and ensure more efficient performance. And we also use it in the automotive industry, where engine blocks, bodies, and rims turn to aluminum to offer stronger yet lighter vehicles. But that's not all. We literally hold this metal in our hands every time we use the case of a phone, a laptop, or any modern technological device that combines design, lightness, and strength. However, the fascination of aluminum doesn't end with the obvious. Its applications reach unexpected and even surprising territories. Consider, for example, pyrotechnics. When burned, aluminum powder generates brilliant silver flashes that illuminate the skies during celebrations and massive spectacles. Or recall the artificial snow we see at ski resorts. Tiny aluminum particles help form crystals that keep the slopes in ideal conditions, even when natural snow is scarce. And if we look even further into space, we discover that aluminum is key to astronomy. Its reflective properties and low weight make it an essential material for telescope mirrors and satellite components, improving the precision with which we observe the mysteries of the universe. Thus, from the soft drink we open in seconds to scientific experiments that seek to understand distant galaxies, aluminum is present, accompanying us at every step, in every object, in every innovation that makes modern life possible, and that connects us with the idea that a light metal, once considered more valuable than gold, today silently sustains much of the world we know. Quality controls are performed at every stage. Dimensions, weight, purity and strength are verified. Only aluminum that meets international standards reaches the market. Furthermore, aluminum has a huge environmental advantage. It is 100% recyclable without losing its properties. Recycling it requires just 5% of the energy that would be used to produce it from bauxite. Thanks to this, much of the aluminum in circulation comes from recycled scrap, making it a key material for the circular economy. In the mid-19th century, this metal was so difficult to obtain that it was considered more valuable than gold, reserved only for scientific demonstrations or luxury items. However, thanks to human ingenuity and industrial processes like Bayer and Hall-Héroult, aluminum went from being a rarity to becoming one of the pillars of modern civilization. Today, this material is present in virtually every aspect of our lives, from the simplest objects to the most sophisticated innovations. It originates in bauxite deposits located in tropical regions, where enormous machines extract tons of the reddish rock. Then, chemistry and engineering transform it into alumina, and finally into the light, shiny and malleable metal we use every day. This journey involves furnaces at extreme temperatures, electrolytic cells that consume colossal amounts of energy, and quality control processes that ensure a reliable final product. The result is a metal that underpins entire industries. It allows us to package food and beverages, erect lighter and stronger buildings, manufacture airplanes that fly higher and consume less fuel, build safer and more efficient cars, and even observe the universe through telescopes and satellites coated with its reflective sheets. Furthermore, its ability to be recycled repeatedly without losing its properties makes it an essential ally in the transition toward a more sustainable economy. So, the next time you use aluminum foil in your kitchen, open a can of soda, or look up at an airplane in flight, remember that behind this everyday object lies an immense journey. The combination of mining, chemistry, electricity, precision engineering, and the dedication of thousands of people around the world. Aluminum is not just a metal. It's a reflection of how creativity and human effort can transform an ordinary rock into a resource that drives development, connects continents, and quietly sustains the modern world.